Okay. And then there's Carlos, Enoch, Lorena, and Bryant, who are geologists at the Institute of Geology in Lima in Peru, helped with the fieldwork aspect of a lot of this research. So there we go. So just a quick overview. The first part is really what the observations side. This is stuff that we're pretty confident about, stuff that we can see. It's what is the pattern of active faulting within the Andes. Second part is going to be a mixture of interpretations. So we're going to look at what does that pattern of faulting mean for the force balance in that region, and what does this tell us about the strength of faults in the lower crust and in the upper crust around the margins of the Andes. Third part is going to think more dynamically about these processes. How can we tell that the force balance or the geometry of deformation in this region has changed? What observations are there for that? And how much has that force balance changed potentially? And then the final part is really the speculative section, where I think about how does this actually relate to the deformation that we see in other global mountain ranges. So just to get us all oriented, what we're looking at here is just a Google Earth image of South America, obviously, and I'm really going to be focusing on this red box, this part of central Peru, where we've got sort of narrow northwest-southeast trending mountain range, and this part of southern Peru, the northern limb of the Altiplano, if you like. And out here, this region that's east of the mountain range, I'm going to refer to that as the South American forelands. So let's get stuck in and actually have a look at some observations. What's going on in terms of the active faulting in this region? Now, the methods that I'm going to focus on using are principally looking at moderate magnitude earthquakes and large magnitude earthquakes in this area. And focusing on these large events is important because if we want to try and synthesize how the entire mountain range is deforming predominantly, we need to look at the big structures, the big faults that are moving the fastest. And kind of in a lot of the history of sort of Andean tectonics, a large amount of the interpretation of the deformation, particularly in, say, southern Peru, has come from observations made from relatively small faults, so things with kind of metric scale offsets, as opposed to kilometric or hundreds of meter scale offsets. So I've kind of taken a slightly different approach, and I've focused really on using earthquakes as observations for deformation in this region. Principally, the two methods that I've been using is quite an old technique now, but it's still a very powerful one, which is teleseismic body waveform modeling, where we try to match the long period P and SH waveforms of moderate magnitude earthquakes using points to determine point source focal mechanisms and centroid depths of these events. And the second technique is using the surface displacements measured through radar geodesy in SAR and inverting those surface displacements for fault geometries and depth distribution of slip on faults throughout this region. These are two pretty well established techniques now, and they're quite powerful in terms of telling us about the geometries of faults, their strike, dip, and rake. So we can get their slip vectors, and we can also get some information about the depth distribution of seismogenesis on these faults. The second technique that I've been using to look at sort of the smaller magnitude range of these earthquakes, so the magnitude 5s and magnitude 5.5s, is by, in general, these earthquakes are too small to generate significant amount of energy within the sort of period band that we need to use for long period body waveform modeling, and surface wave methods to determine focal mechanisms for these earthquakes through things like the GCMT are often reasonably poor because the signal to noise ratio of these earthquakes is generally quite small. Because they're small earthquakes, they don't generate a large surface wave field, a large amplitude surface wave field. So I've been focusing on trying to get the depths of these earthquakes by modeling their vertical component, broadband and short period seismograms, and trying to match the shapes and the travel times of the direct wave, the P, and the surface reflected depth phases, the little p, big P, and little s, big P. And the reason why I'm interested in these small earthquakes is that they can fill in a lot of the gaps in terms of the depth extent and the depth distribution of seismicity within the Andes. Okay, so when we actually combine all those techniques together, what we can do is construct some really quite detailed maps of how sections of the Andes Mountains are currently deforming. And what we're looking at here is a region of central and southern Peru and northern Bolivia. So this is just that northern limb of the Bolivian orocline. Here's Lake Titicaca. Off here, we've obviously got the Peru-Chile Trench, the Nazca subduction zone, Nazca plate subducting underneath here. And plotted on top of this are the whole bunch of focal mechanisms that have been studied using either the radar geodesy or through that body waveform seismology technique. And we can see there is a huge amount of detail in here, and there's quite significant along strike changes in the way in which the mountain range and its margins are deforming. And kind of unusually for a talk on the Andes, I'm not really going to talk very much about the subduction zone, and that's because in general the subduction zone earthquakes, or at least their kinematics, are relatively simple. All of the slip vectors on these big megathrust earthquakes that rupture the western margin of South America, the subduction interface, typically have slip vectors that are within a few degrees of the Nazca South America relative plate motion, and they're just breaking the subduction interface. When we actually look in the top of the mountain range, what we can see is there's significant along strike variability in the way that the top of the mountain range is deforming. So up here in the Cordillera Blanca, in the sort of central part of the high Peruvian Andes, there's an earthquake in the 1940s that has a few sort of pretty dodgy analog seismograms. People have been able to derive focal mechanisms from these for this particular event. There's also really beautifully preserved fault scarps here that tell us that this region is extending in a roughly east-west direction. And that changes as we move towards the southeast along the mountain range. In this area, a place called Pariahuanca, there were 2 earthquakes in the top of the mountain range that magnitude 6.5, and they ruptured in oblique transpressional, so basically predominantly reverse faulting earthquakes. Moving further southeast, and we move into this region kind of transitional between the northern part of the Altiplano and central part of the high Andes, there's a whole bunch of strike slip faulting earthquakes in this area. So we've got another change in the kinematics of the deformation. Moving further southeast again, we get another change. So southeast of Cusco, what we find is there's a whole cluster of normal faulting earthquakes, magnitude 5, magnitude 6 normal faulting earthquakes, that have roughly northeast-southwest oriented slip vectors. They're accommodating northeast-southwest extension in this region. And if you move southeast further again, further along strike the mountain range, down into the Bolivian Altiplano, what we can see is there's actually very little evidence of active deformation through seismogenic slip-on faults in this region. There's almost nothing going on that we can see using earthquakes. If we look on the eastern margin of the mountain belt, so we've just been along the high ridge line, if you like, at the top of it, if we look along the eastern margin, what we see is there's similar long strike variability in the mechanisms of earthquakes in this region. So up here in central Peru, what we can see is that there's a whole bunch of relatively deep earthquakes. So they extend from the surface up here about 5 kilometers down to 30 kilometers in some cases, and even down to 42 kilometers here east of the shear uplift. And this is telling us that pretty much the whole crust in this region, so the crust is about 40 kilometers thick here, or based on receiver function data, the whole crust in this region seems to be seismogenic and is deforming in earthquakes as it's shortened on the eastern margin of the Andes. As you move further southeast and we move into the sort of northern part of the of what's often called the sub-Andean fault thrust belt, what we can see is that there's actually low angle thrust in this region. There's very few earthquakes, but the orientation of shortening on this low angle thrust in this region around Cusco is actually north-northeast, south-southwest. The slip vector for this earthquake is north-northeast, south-southwest. And that's obviously very much rotated from the roughly east-west slip vectors on the reverse faulting earthquakes here, and is also rotated relative to the earthquakes that further southeast along the sub-Andean fault thrust belt. So if we move along strike, we can see that the slip vectors rotate. So here we've got north-northeast, south-southwest shortening. Here it's roughly northeast-southwest. Here it's roughly northeast-southwest. And over here, down south of Santa Cruz, it's roughly east-west. So what we can see is that there's really quite significant along strike variability in the way that the high part of the mountain range is deforming and the way that the margins of the mountain range are deforming. And in particular, what's kind of previously not really been appreciated is the fact that the shortening on the eastern margin of the Andes is essentially perpendicular to the strike of the mountain belt. So it's parallel to gradients in topography in these regions. It's not parallel to the Nazca South America relative plate motion. And what I'm going to do is try and use these observations to say something about the forces that are controlling the pattern of deformation in this area. But one of the things we don't really get much information about from earthquakes alone, just because they sample kind of snapshot of sort of multiple episodes of deformation. So they're only really sampling the last 30, 40 years of deformation in this region, in this area, as opposed to the sort of million-year timescale, is that we don't get any real idea about the long-term rates of deformation. So what I'm going to show you next is a bunch of observations from the field where we actually traveled along this area of normal faulting between Cuzco and just to the south of Lake Titicaca. And we actually were interested in trying to work out how fast and what was the distribution of the normal faults in this area that are rupturing in these normal faulting earthquakes. So how fast are these faults moving, and how fast is the extension that they're accommodating across this section of the Altiplano. So here's just a Google Earth satellite image of that same region. Here is Lake Titicaca, and up here, this little gray strip is the Cuzco Basin. And these red lines are kind of hastily drawn faults that we were able to visit and to map and study in some fieldwork back in 2018. And what we can see is it's kind of a northwest-southeast trending normal fault system. And what I'm going to show you is some observations from a bunch of different localities along this fault system. And I'm going to describe how we were able to measure the kinematics of these faults, so the orientation of slip on them, and also how we were able to say something about the rates of motion across these faults. So zooming in on that big red blob, this is the first locality, or one of the first localities I'll show you, which is a place called Sangarara. And this is a beautifully preserved normal fault scarp that's outcropping at about 4,000 meters above sea level. And we can see there's the obvious kind of uplifted footwall, and this thing's kind of 500, 600 meters high relative to the hanging wall basin. And you can see there's these kind of classic triangular facets along the trace of the fault. And the hanging wall basin in this area is actually being quite deeply incised by rivers that are cutting across it. So you can just see a hint of a little canyon that cuts through this sort of hanging wall fan surface in this area. What we also found was that there were little snippets of fans preserved within the footwall of this fault. And this is super handy if you're interested in trying to estimate the slip rates on these structures and the horizontal extension rates across them. So here's a Pleiades stereo DEM. So this is just formed using two Pleiades images and using kind of stereo photogrammetry methods to form a high resolution digital elevation model of this area. And it's being colored in hill shades. So this is what this kind of grayscale color looks like. And you can see that in this region at the kind of northwestern tip of the fault, we managed to identify an area where there was this little sort of snippet of fan surface that was preserved and had been uplifted and offset relative to the hanging wall fan surface. And both these fans were incised. That's telling us that they've been abandoned. Sedimentation is no longer taking place on the surfaces necessarily. And we were able to date this fan surface based on using radiocarbon dating of some organic soil layers that sort of sit and intercalate with the top of the alluvial gravels. And we were able to measure the offset of the fan surface using this high resolution DEM. So this is on the left here, this is just a topography profile through across this fan surface from the uplifted footwall to the hanging wall. And you can find that it was vertically offset by 30 meters, and the kind of bound on the age of the surface of this fan is about 7,000 to 8,000 years old. If we actually want to calculate what this means for the rate of motion on the fault and the horizontal extension rate across the fault, what we need to do is actually have some knowledge of the geometry of the fault and its slip vector. And thankfully, this is Aisling stood in front of a really beautifully preserved exposure of this fault plane in one of these gullies that was cut across the fault scarp. And we were able to measure the slicken lines and the fault geometry on this surface. And therefore, we could calculate that the fault had a throw rate of about 1.5 to 3 millimeters per year, and a horizontal extension rate across it of about 2 to 4.5 millimeters per year. So this is kind of surprisingly quick, I would say, given that it's generally previously been assumed that there's very little deformation occurring within the top of the high Andes in studies for using things like GPS, for example, to try and map patterns of coupling on the subduction zone. So if we kind of put that into context with a bunch of other observations that we had from up here around the Cuzco Basin, what we could see was that the extension across this normal fault system was predominantly north, northeast, south, southwest, and it was occurring at rates somewhere between 1 and 4 millimeters per year. So moving further southeast, what I'm going to show you now is some observations from a locality down here. It's a place called Parina, and it was an area where this fault ruptured in an earthquake back in 2016. So we're pretty confident this thing is active. So here's just a sort of classic Peruvian field photograph with your various sort of assortment of llamas and alpacas in the background. And you can see here in the foreground, this is the surface rupture trace from this earthquake in 2016. this is a really interesting structure because the drainage here is actually running from the hanging wall basin and then sizing across the footwall. And the footwall escarpment itself is only maybe 100, 200 meters high. So that's telling us that essentially the large scale relief across this structure is far less than what we saw at many of the faults on the northwestern edge of this normal fault system. And the kind of general interpretation of that is either that these faults are moving more slowly, or that they've become active more recently in the sense of normal faults. So we were able to find localities along this structure where late glacial maximum moraines were actually offset, the crests of the moraines, and use high resolution DEMs built from drone photogrammetry to estimate the offsets of these moraine crests. And we used beryllium-10 dating to estimate the ages of those moraines. And they were about 10 to 15,000 years old. And we could use those to essentially estimate the fact the slip rate on this fault is about 1 millimeter per year. So the horizontal extension rate is a little less than a millimeter per year, given that it dips at about 45 degrees. So it's slightly slower than what we saw on the northwestern side of this normal fault system. The other thing that we identified is that a lot of these structures where there's active normal faulting previously were active as reverse faults. So in a lot of these places, we have older rocks basically exposed within the hanging wall and younger rocks within the footwall. And that's telling us most of these things were previously active as reverse faults. And the trend of this normal fault system actually follows the trend of a well-mapped reverse fault system called the Cuzco-Lagunitas fault system. So if we kind of compile that information again, stick it on our previous graph, what we can see is that we have this extension that seems to rotate clockwise ever so slightly as we move towards the southeast, and the rates of extension seem to decrease as we move towards the southeast, towards Lake Titicaca. So the final place I'm going to show you some observations from is just right down here in the southeast at a place called Wea Wea. So here we just have a field photograph. There's someone highlighted here for scale, and we're looking along one of these faults that we managed to identify. And you can see that it's extremely subtle in this area. There's a very slight reversal in this local slope direction, which is trending from the right-hand side to the left-hand side. And there's essentially this little bump in the landscape that's uplifting the downstream side by maybe a couple of meters or so. And so this is far, far more subtle than what we saw at Parina, and far, far more subtle than what we saw at Sangrara, where we had that beautifully exposed sort of 500, 600 meter high footwall escarpment. So altogether, the inference is that there is this normal fault system that is cutting obliquely across the Altiplano. It seems to be following the trend of a previously active reverse faulting system that's thought to have been active about 16 to 5 million years ago, and has since been kind of inverted in a normal sense, in an extensional sense. And the direction of the extension on these normal faults seems to rotate from being roughly north-northeast, south-southwest, up here in the northern part of the fault system, to being northeast-southwest, and the extension rates die off towards the southeast. Okay, so that's a sort of summary of what new observations we've been able to make of the active deformation in this particular interesting section of the Andes and within the Altiplano of southern Peru. So the next thing to do is to ask the question, what does this mean for the current balance of forces that are controlling that pattern of deformation in this region? So there are a few observations that we can make that tell us something interesting about what's probably the dominant force sort of contributor to the deformation here. First thing is that we noticed that the direction of extension on this normal fault system rotated as we went towards the southeast, and this rotation seemed to roughly mirror the pattern of the rotation in the shortening slip vectors on the eastern margin of the mountain range. So we can see that up here, the extension is roughly north-northeast, southwest, and the shortening along the margin of the mountain range is north-northeast, south, and southwest. The second thing we can see is that the direction of extension is parallel to the direction of shortening across the margin of the mountain belt, and the fact that we're actually having extension in the top of the mountain range itself. And these are all telling us that probably it's the buoyancy forces due to crustal thickness contrasts and contrasting gravitational potential energy between this high region of the Altiplano and its margins, the South American forelands and the trench down here, that are really controlling the orientation of the extension in the high ground and the shortening within the low ground along its margins. It's not necessarily parallel to the directions of relative plate motions in this region. One thing that really simplifies the picture and means that we can do some interesting force balance calculations in this region is the fact that all the deformation is predominantly in plane strain. So if you sum the moment tenses of these earthquakes in this region, you find that the across strike extension is about 20 times larger than the along strike shear. So that means that we can basically treat the force balance in 2D. If we were to take a cross section through this region, all the deformation is going to be predominantly within that cross section. So looking at one of those cross sections and thinking about it in a sort of slightly cartoonish but really quite informative way, it looks a bit like this. So, I mean, we've got the South American fallings out here. We've got earthquakes extending all the way throughout the crust in this region that are breaking in reverse faulting earthquakes and some strike slip faulting earthquakes down to about 42 to 45 kilometers. And the upper mantle seems to be potentially seismogenic a few kilometers into it, but it's difficult to tell based on the receiver function data that we have. It's then separated by the mountain range by this kind of fallen basin where we have low angle thrusts in some places along the margin of the mountain range, but in some places steep reverse faults. And then in the mountain belt itself, we've got this low relief, high elevation plateau that has a relatively thin seismogenic layer, about 10 kilometers thick, and it contains normal faults. And those normal faults are telling us that the buoyancy forces in this region, generated by differences in essentially crustal thickness contrast between these two areas, exceed the horizontal forces that are acting through the fallen lithosphere. And this is really important because it's going to allow us to actually place bounds on the mechanical properties of faults in the fallen lithosphere. Because if we can place an upper bound essentially on the size of this horizontal force acting through the fallen lithosphere out here, and we know that the faults out here are rupturing in earthquakes, that's telling us that this force is large enough to break these faults, and therefore we can estimate the static frictional resistance to slip along these structures. The final thing just to think about is what the geological conditions of the faults that we're actually probing in this region. So other localities where we've been able to see lower crustal earthquakes along the margins of high continental mountain ranges typically have been interpreted to mean that the rocks down here in the lower crust must be extremely cold, certainly less than 600 degrees Celsius, and relatively dry, and by that I mean less than about 0.05 weight% water. And that's because if these rocks did contain, or were very hot, or did contain large weight fractions of water within the phase assemblage, then typically that would mean that these rocks would be able to deform through temperature-dependent creep mechanisms, things like diffusion and dislocation creep, and that would preclude the accumulation of elastic strain at these depths, and therefore you would be able to generate magnitude 5, magnitude 6 earthquakes over sort of 5 by 5, 10 by 10 square kilometer fault planes. So what I'm going to do is show you how we can estimate the size of this buoyancy force. I'm going to show you some estimates of how strong the faults out here in the fallen lithosphere have to be, or what an upper bound on their strength must be. And then I'm going to make some sort of interesting conclusions about what that might mean for the geological conditions in the lower crust, and what that means, what's controlling the strength of faults within these settings. So the first thing to do is actually to calculate the size of that buoyancy force. And this is just a plot showing you a result of a suite of these calculations. So essentially what we do is numerically integrate differences in the vertical normal stresses between the mountains and the fallens, and perturb the temperature structure, the crustal structure, the lithospheric mantle structure, the amount of chemical depletion in the lithospheric mantle, the thermal expansivity of the rocks, all which change the density structure in these areas, and therefore would affect the size of the buoyancy force. And the appropriate range of values that we find for the Andes is somewhere, for the buoyancy force, is somewhere between about 4 and 8 teranewtons per meter along strike. And this per meter along strike is because we're treating it in two-dimensional cross-section. So this is an upper bound on the size of the horizontal force acting through the fallen lithosphere. So the second part of this, sort of these calculations, is to work out how weak must faults be in order to be slipping in earthquakes in response to those forces. So this is what's shown here. This red swath basically just outlines, again, a sort of density plot of a range of different models in which we perturb a range of different values, like the depth of brittle ductile transition, etc. And what we're looking at on the x-axis is the effective coefficient of friction on faults within the seismogenic layer. And on the y-axis is the horizontal force that the lithosphere could support, given that effective coefficient of friction on faults within its crust. These horizontal black lines here are the bounds on the size of the buoyancy force that we estimated in the previous section. And what you can see is that in order for essentially the fallen lithosphere to be breaking in earthquakes in response to these forces, requires that the effective coefficient of friction on faults within the crust must be less than about 0.12. And to get an absolute upper bound, what we can do is completely ignore the strength of the lithospheric mantle altogether, or completely ignore any creep strength within the Earth's lithosphere altogether, and assume that all the force is supported by faults. And that sort of pushes this red swath curve slightly towards the right, and we find that an absolute upper bound is about 0.2. And this is equivalent to faults within the lower crust supporting average shear stresses less than about 150 megapascals under conditions confining pressures on the order of 0.8 to 1 gigapascal. So kind of why is that interesting? Where's that got us? We've been able to estimate forces, we've been able to estimate how strong the faults might be in this setting, an upper bound on how strong the faults must be. But why is it interesting? It becomes interesting when we compare it to other geophysical estimates of rock, at least fault strength, that come from either laboratory estimates or from estimates of fault dip distributions, other force balance type methods like I've shown here, and also proxies, so things like paleopiezometry or earthquake stress drops. What we typically find is that across the board, all these geophysical estimates suggest that the effective frictional strength of faults is relatively low, less than about 0.3, and this is the static friction. So this is the sort of stresses required to get the fault to break in the first place. So I'm not talking about dynamic friction here. And in general, these low values of the effective friction compared to the sort of intrinsic friction estimates based on things like Byerlee's law, it's been interpreted to suggest that faults either contain large amounts of suprahydrostatic pore fluids, in some cases supralithostatic, and they also contain potentially sort of interconnected weak layers of intrinsically weak minerals like phyllosilicates. And there's plenty of evidence that these conditions exist in the shallow crust. There's lots of evidence for phyllonitized fault cores on upper crust and mid-crustal fault zones that have been exhumed. And there's plenty of evidence that there's potentially even supralithostatic pore fluid pressures within the mid and upper crust based on things like horizontal vein suites that require fluid pressures larger than the overburden pressure. But one setting where we don't necessarily have geological evidence for either intrinsically weak minerals in those conditions or very large amounts of highly pressured pore fluid is within the lower crust that we expect to be these granulitic kind of analog lower crustal terrains that we expect to be forming the lower crust that we see on the margins of mountain belts in order for seismogenesis to take place at depths of sort of 30 to 45 kilometers. And this is the setting in which we've inferred there to be actually relatively weak faults in this study. So when we actually look at analogous terrains for what we think is happening, what we think is kind of comparable to the lower crust beneath South American forelands, examples for these include places like the Bergen Arcs or the Musgrave Ranges in Central Australia and parts of Arctic Canada. The rocks there are typically granulitic, so they're metastable. They were formed under much higher pressure and certainly much higher temperature conditions, and they are extremely dry because they were formed as a product of melting, which stripped all the water out of them. So that means that it's basically very difficult to have any free water phase in these rocks because water will be rapidly used up in retrogression reactions in forming new stable mineral assemblages. These rocks also essentially contain no pore space, they're very low permeabilities. So whether you can even have something like an effective pressure that exists in these rocks seems very unclear. And the modal fraction of phyllosilicate minerals in these rocks is generally very low. That's just because these things, phyllosilicate is typically hydrous phases. And if there's no water, then you can't form hydrous phases in these rocks. So I think this kind of leaves us in an interesting position where the mechanisms that we've invoked to be forming or to be weakening faults within the upper crust and the mid crust haven't necessarily been observed to be present within the lower crust, but we do know that I think that we can argue that lower crustal fault zones must also be weak. They must also have low effective friction, static friction, but they also must be seismogenic in some areas. So one interesting aside that we can also probe with our observations from the Andes is the fact that in a lot of these lower crustal rocks that have been exposed at the surface now, deformation typically seems to lead to rapid ductile overprinting. of previously brittle fabrics. So by that I mean these two examples up here on the top is just a field photograph and a photomicrograph from pseudotacholites that formed, led to grain size reduction and maybe a small amount of water ingress, and have been rapidly overprinted by ductile shear. And that would suggest that essentially as soon as you start to move faults, reduce grain size, or drive water in from maybe upper mantle or mid-crustal localities, this rapidly leads to a switch from brittle to ductile deformation in these types of rocks. But when we look at observations of areas where there are currently lower crustal earthquakes along the eastern margin of the Andes, these are also regions that have undergone a kind of protracted history of rifting and shortening. So this is just a swath of, a cross-section, of earthquake depths from the Sierra Pampeanas in Argentina, and a swath of earthquake depths from the Huallaga Basin in central Peru. And what we can see is that there's a whole bunch of lower crustal earthquakes in these regions, and at the surface, there's plenty of geological evidence that these regions were previously Mesozoic rifts. So this is based on subsidence data of the stuff that's now been squashed and shortened in these regions. So if these areas were previously undergoing rifting, and now they're undergoing shortening, then presumably they've undergone deformation within the lower crust, but the lower crust still seems to remain relatively seismogenic in these areas. So I think this raises some interesting questions about how can regions that have had a protracted history over tens of millions of years of stretching, rifting, and shortening, for example, remain seismogenic if deformation typically leads to grain size reduction and fluid ingress along fault zones. Okay, so that's kind of all I wanted to talk about in terms of the static force balance and what these observations of active deformation can tell us about the forces acting through the lithosphere and how we can use that to make some interesting observation or interesting interpretations about the mechanical properties of faults within the South American fault and lithosphere. The second thing I want to talk about is what observations we have and what might have led to a change in the force balance in southern Peru. And the reason for thinking about this is that, remember, lots of those normal fault systems that I talked about were actually previously active as reverse faults. So that's telling us there's been a change in the kinematics of deformation in that region. It's also a high and wide low elevation plateau. And plateau have a very specific sort of method of formation, or we think they have a relatively simple method of formation. I think this model of plateau generation from Molnar and Lian Chen is extremely powerful tool for us just to think about. It's very simple, but very powerful for us to think about how mountain belts might evolve through time and how we might have gone from a stage of reverse faulting in the southern South Peruvian altiplano to normal faulting. So what we can see is that this model basically says you have the deformation state within the mountain ranges is dominated by a balance between two predominant forces: the force acting through the fallen lithosphere that's squashing the mountain belt, and the buoyancy forces due to crustal thickness contrasts between the mountains and the falllands. And early in the history of mountain belt evolution, the mountains might be relatively low, so they might have relatively low small buoyancy forces relative to the horizontal force acting through the fallen lithosphere, and that would lead to compression, shortening, and associated isostatic uplift of the mountain belt. After time, this will essentially lead to a balance between the buoyancy forces and the horizontal force acting through the lithosphere. And when you reach that stage, you would expect there to be a change to strike-slip deformation in the top of the mountain range, and for the mountain belt to start to step out and shorten material along its margins, because it requires less work to shorten material at lower elevations than it does to shorten material within the high elevation, the high plateau. And this will eventually progress through time and lead to a wide plateau if the balance between these two forces remains relatively similar. So in order for there to be extension, presumably there must have been a change in this balance. Either the buoyancy forces must have increased, the geometry of the deformation may have changed, or the forces acting through the fallen lithosphere might have decreased. So our observations from the Andes can actually, they tell us that the force balance must have changed because this region was previously shortening, it's now extending, it's now collapsing, if you like. And it's telling us that, that this is happening in different places in different ways along strike. And what I'm going to do is I'm going to use these observations, use different geological observations along strike to make an argument that the cause of the onset of extension in these two sections of the mountain range and the cause of the sort of decay in the shortening rate within the Bolivian altiplano might have been due to a change in the horizontal forces transmitted across the eastern margin of the mountain belt in this area. So I'm going to show you a compilation of some active deformation measurements and also geological observations along this particular profile, this red line, that's going to allow us to sort of synthesize all this information together. So what we're looking at here is, on the bottom, we're looking at a swath of the elevation of the mountain range, the height of the mountain range along its spine as a function of latitude. So this is the sort of latitudes of central Peru, southern Peru, the Bolivian Altiplano, and the Puna Plateau. And sort of summarized down here is a whole bunch of different observations from paleoaltimetry and from geological observations of the timing of the onset of either extension or the decay and shortening rate, for example, here in the Bolivian Altiplano. That tell us something about the timing in which the mountain belt switched from a state of extension, shortening, to a state of extension. Shown on the top here are these little blue and green bars, and these are telling us what is happening in the top of the mountain range right now. What is the current active kinematics of deformation in this region? So you can see there's these extending areas, places like the Cordillera Blanca, Cusco-Lagunillas fault that I've talked to you a lot about in this talk. And there's a switch from extension to shortening to extension to shortening to extension in different places along strikes. And this is interesting because shortening and extension both occur in places that are very, very high sections of the mountain range. So it doesn't look like the elevation of the mountain range, which is essentially a proxy for the buoyancy forces acting on the mountain belt, is the only cause of regions that are currently extending. There must be something else happening. And what we think is that something else is to do with the way that the foreland and the eastern margin of the mountain belt is currently undergoing shortening. And that's because in areas where we see a shift from extension to shortening, typically correlate with areas where we've got very steep reverse faults rupturing to the surface essentially as basement uplifts on the eastern margin of the mountain belt. So a good example is this region here, where this deformation in the top of the mountain range switches from extension to shortening, and over that same area we get a switch from sort of low angle decollements in the fall and fold thrust belt that may be underlain by steep reverse faults, but there's at least some kind of decollement surface present, some sort of decollement horizon present. And then it switches to where we have a basement uplift, essentially along the shear uplift. And we can see that this thing is rooted in the lower crust based on the earthquake depths that we've been working on. So the other thing that we noticed is that the rough timing of the onset of extension in the top of the mountain belt, and this is a very rough chronology, seems to kind of correlate with the timing of the onset of exhumation within the fold thrust belts along the eastern margin of the mountain belt. So if we kind of compile all this together into a schematic view of what might be happening or what might have happened, is that at some point in the past, the mountain range was undergoing shortening within its interior as the horizontal force acting through the fallen lithosphere could transmit enough force into the interior of the mountain range to overcome the buoyancy forces and put it into a state of compression. And then at some point since then, the mountain range reached its limiting elevation, begins to step out into the thick fallen basin sediments that form along the margins of the mountain belt. And in these fallen basin sediments, we have relatively weak decollement horizons that reduce the shear tractions acting along the base of the upper crust, essentially, reduce the horizontal force acting through the upper crust, or the horizontal force that you can transmit from the fallen into the mountain belt. And that could have led to the onset of extension. And this would explain the sort of relationship between the thin-skinned fold thrust belts that we see in the areas of the mountain range that are extending, and also the rough timing of the onset of extension. But I think there's a lot more work to be done to sort of pin down when these normal faults actually started to move through, for example, dating the sediments exposed within their hanging wall basins. But I think we can go a little bit further than that because we actually have observations of how fast the mountain range is extending. And here's some really neat numerical models, 2D numerical models from Babejko and Sobolev that sort of encapsulate the dynamics of what we were trying to, what I was interested in trying to replicate. So on the top here, they just is a case where you have a sort of crust, a fallen crust formed of felsic crust and a mafic crust, and you indent it into a weak plateau, basically. And you generate shortening within the plateau. And then below here are two different cases for the type of shortening, distribution of strain within this setting. If you try and drive shortening at a constant rate, if you have a layer of sediments on the top of the foreland, or if you have no sediments on the top of the foreland, basically. And what they found was that to drive this kind of simple shear or thin skin style deformation required the same rate as you would want to drive shortening in this system, the thick skin system, requires lower forces, horizontal forces, basically. So if you were to imagine if you were to go from this thick skin state, dump a bunch of sediment on top of it, and allow strain to localize into that weak sediment pile, you would reduce the horizontal forces needed acting through the lithosphere in this region and transmit it into the top of the plateau. And given that we have estimates of the extension rate in the top of the plateau, and we have some kind of knowledge about the material, the average material properties of the material beneath the plateau based on the relationship between buoyancy forces and strain rates from the plateau from work of people like Simon Lamb, what we can actually do is ask the question, how much must the horizontal force acting through the boundary, the eastern boundary of the mountain range decreased in order to explain the current extension rates that we see in the plateau that we were able to measure across those active normal faults. So here is just a result of these very simple analytical calculations. On the x-axis is the strain rate within the interior of the plateau. This is the horizontal extensional strain rate, and this is just taking the slip rates on those faults and averaging over the width of the plateau. And on the y-axis is the viscosity of the material within the plateau interior. And this is, generally pretty poorly known, but I'd say it's reasonably well constrained to be within this order of magnitude, if you like, based on a bunch of other work by people like Simon Lamb and Laurent Husson. What we find is that the range appropriate for the Peruvian Andes tells us that the horizontal shear force acting on the base of the subandean wedge must have decreased by about 0.45 to about 0.7 teranewtons per meter. And that's less than about 10 to 25% of the total horizontal force balance across this region. So the implications of this work are that really subtle changes in the material properties, and particularly the integrated strength of faults along the margins of the mountain range, might actually lead to perturbations in the deformation state of the interior of the mountain range. And these might be quite small, but we can actually use the coupling between the two to place constraints on the time evolution of dynamics, potentially in continental mountain ranges. So what are the kind of wider implications for that? I've talked a lot about some new observations, then I've talked about the interpretations this has, the interpretation that this might mean for sort of forces going on in this region, and force balance in this region, how this might have changed. But what's going on in other mountain ranges, and how can we synthesize the kinematics that we see in the Andes with what's going on in other global continental mountain belts? And are the same processes that we think are happening in the Andes happening in other settings? Well, the first obvious place to look is always at southern Tibet. For some reason, it attracts the most attention. And in southern Tibet, there's been a very clear shift in the kinematics of deformation over the past sort of 30 million years or so. About 30 million years ago, 20 to 30 million years ago, there was exhumation occurring along the South Tibetan detachment system, which was a normal fault that was accommodating roughly north-south extension across this area, so it's range perpendicular extension. And that's changed more recently and is now overprinted by north-south trending normal faults that are accommodating east-west extensions. That's range parallel extension. So that's telling us that the kinematics of deformation in this setting has changed within the past 20 million years or so. So it's interesting to see that we've had similar shifts and similar changes in the kinematics in this particular setting. A second place that I'm just going to talk about is the Albanides, which are on the eastern margin of the Adriatic Sea, just east of Italy, and Albania, Greece, and Montenegro. And what we're looking at here are the focal mechanisms for earthquakes in this particular section of the Albanides. And we can see that along the coastline, there's a bunch of low angle and sort of reverse faulting earthquakes. They extend down to 20 kilometers depth or so. And within the mountain range, which is about 1,000 meters high on average, there's east-west extension happening that's parallel to shortening along the margins of the mountain belt. So this is very similar to the kinematics of deformation that we see in the Andes. So it looks like there are analogous terrains to what's going on in the Andes Mountains. And the final setting that I'm just going to introduce is the intracontinental mountain range of the Tian Shan. And this has been a really well-studied region actually over the past 20 years or so. And what we found is from the earthquake data that there's still active shortening that's kind of distributed throughout the interior of the whole mountain range. So you can see here in the western part of the Tian Shan, we've got earthquakes on the margins of the mountain belt, but also earthquakes in the interior. And this is corroborated by evidence for active shortening from quaternary geomorphology for active faults presently accommodating shortening on the rates of a few millimeters per year within the interior of the mountain range. And GPS also sort of confirms that the interior of the mountain belt is still shortening. So when we think about all these different settings and all these different deformation or kinematic styles in this one framework where we can think about this balance between buoyancy forces and the horizontal forces acting through the fallen lithosphere, what we could speculatively do is put together a kind of progression of deformation within mountain belts as either finite shortening progresses or time progresses or something changes within the mountain range. And early stage mountain ranges might look something like the Tian Shan or the Laramide might have looked like, where we had sort of steep reverse faults along the margins of most of the mountain belt and active shortening within its interior. And that's when the horizontal forces acting through the foreland, in this case through the Tarim Basin and the Kazakh platform, are large enough to overcome the buoyancy forces generated by the thick crust within the mountain range. And that will progress through time if shortening continues until a stage where the mountain belt starts to step out, and it steps out into its weak fallen basin sediments. And at that point, you might expect a stage where you get extension, east-west extension within the mountain range, in this case within Albania, that's parallel to shortening within the fall. So you might get a switch from shortening in the mountain range to extension in the mountain range, and that extension parallel to shortening along its margin. And then as shortening progresses and the buoyancy forces continue to dominate the pattern of deformation along the margins of the mountain belt, you might expect that sort of gravitational spreading leads to a divergence of the radial thrust vectors and along the margin of the mountain belt, and will eventually then lead to a switch into which you get a long strike shortening. So this is a kind of speculative model, but it's something that seems to be able to explain the differences in lots of intracontinental and ocean continent mountain ranges with actually very simple physical principles in which all we're thinking about is this balance between foreland, the horizontal forces acting through the foreland and being transmitted into the thick crust of the mountain range interior. Okay, so I mean, this is just a slide with the conclusions on, and I've hopefully convinced you, firstly, that there's good evidence that active normal faulting is occurring in the South Peruvian Altiplano, and that the orientation of the extension on those normal faults mirrors the rotation in the shortening direction along the eastern margin of the Andes. I think this is a pretty nailed-on observation, if you like. Then the interpretations were that we were able to use that pattern of deformation to estimate the size of the horizontal forces acting through the lithosphere on the margins of the Andes. And we could use that to say some quite interesting things about the static effective friction along faults within the lower crust. And it suggests that they were supporting, or at least rupturing, in earthquakes at relatively low shear stresses and resolved shear stresses. And that raised some interesting questions about what is actually controlling the material and the rheological properties of lower crustal faults. And then one thing I think gets slightly more speculative is when we think about what's actually caused the change in the force balance, but what is consistent with the timing of changes in deformation and also the amplitudes of the change, the kinematics of the deformation, is that there might have been some change in the horizontal forces acting along the eastern margin of the mountain range. And this might have been about 10 to 25% of the total horizontal force balance. So we find that potentially mountain ranges are extremely sensitive to the integrated strength of faults along their margins. And then the final section was really about how can we synthesize the observations from the Andes with what we see in other global mountain ranges. And I think this is something that requires a lot more work, but it's interesting to start thinking about these questions and to try and expand our ideas of what's happening in the Andes and think more holistically about mountain ranges in general. Okay, so with that, I'll have a look at questions. So look, can I see the chat? Okay, so we've got a question first from Patricia Alvarado, and it says, I'm curious about the part of the fault in red trace making shape as a comb, where the main extension axes are rotating along strike. What role do these comb faults play in the deformation? So I presume that's referring to the change in the orientation of the normal faulting, the direction of extension of the normal faulting. I think I explained why we think that changes its orientation, and that's because the curvature of the mountain range means that the essentially horizontal gradients in pressure within the lithosphere will vary along strike, and the extension should be parallel to the gradients in topography along the margin. If you think about it as deforming as what's often referred to as a gravity current, if you like. So the deformation, essentially the middle of the mountain range is being stretched by shortening along its margins that also rotates along strike. I don't know if that actually answers your question. I hope it does. Sorry if it doesn't. We've got one from Francisco Delgado. So it says, thanks. Compared to the Zagros and the Himalayas, very few geodetic and seismic studies of active crustal faults in the Andes. Very true. There is notably a lack of earthquakes in the Altiplano detectable at teleseismic distances. That's kind of true. I think I've shown that there are a number that are detectable. In your view, what do the Andes seem to be less active compared to the Himalayas, or is it biased view based on lack of data? I mean, probably the reason is because the vast majority of the deformation is accommodated on the subduction zone. The shortening rate in the back of the Andes is probably 5 millimeters per year, so shortening rate on the southern margin of the Himalayas is 20 millimeters per year. It's also a much larger area is the Himalayas, so you might expect there to be more earthquakes over a larger area. But I think that's an interesting question. Certainly why the Bolivian Altiplano seems to have very, very little active deformation. I reckon it's probably because it's just lower on average. So the buoyancy forces in that region are less than they are in, say, southern Peru. Southern Peru is actually the highest on average section of the Altiplano, as far as I can tell. We've got one question from Gorky Ruiz. Do you have any GPS velocity fields to see how the current rotation is shortening in the central Andes? And in your modeling, have you included the Nazca Ridge flat slab subduction? No, I mean, I have looked at so the interesting thing about the GPS velocity field is that it shows that this whole area where we see active normal faulting is actually undergoing incremental interseismic shortening between major megathrust earthquakes. So that's telling us that these normal faults in the top of the Altiplano are actually undergoing incremental shortening across that region. And this is probably just elastic compression of the overriding plate between large megathrust earthquakes. But it's interesting to think about what this means for permanent deformation within the plateau at lower crustal depths, because over long time scales it's extending over sort of the past at least 2 or 3 million years, but over short time scales between megathrust earthquakes, which is the predominant time span of the megathrust earthquake cycle, is actually undergoing shortening. And the reason for the kind of mechanics of what's going on in the sort of mid crust of the Altiplano as this shortening goes on and within the sort of elastic part of the shallow crust, I think is quite an interesting question, but you probably need to use some quite clever numerical techniques to address what's actually going on there. The flat slab subduction doesn't seem to have much effect on where the region, which part of the mountain range is extending. You can see there's flat slab subduction underneath the Cordillera Blanca. There's no flat slab subduction underneath the section of southern Peru. There's lots of really nice work that's come out of people like Beck and Zant's work in that region to map the geometry of the subducting slab. And it seems the flat section seems to stop just at the northwestern edge of this normal faulting system. So I think the flat slab, presumably there's just a very weak layer between the slab and the overriding plate. That means that there's very little effect of horizontal tractions from the flat slab on the base of the overriding plate. I think that's something people have invoked for Mexico as well. Peter van der Beek, haven't discussed a potential role for altiplano uplift found from lithospheric foundering in your model. Although disputed, there appears to be evidence for late Miocene uplift in the northern altiplano. How would that affect the stress field? Yeah, I mean, that's exactly a great point. The reason why I've kind of not thought so much about delamination or lithospheric foundering or whatever you want to call it is partly because of the effects of subduction and the presence of the flat slab, for example, underneath the section of the central part of Peru. I mean, if there's a flat slab underneath, then the lithospheric mantle can't go anywhere. It's got to be either pushed away or it can't founder. Other places where people think there's lithospheric foundering, like central Tibet and delamination, there's evidence that the lithospheric mantle in those regions is chemically depleted and therefore buoyant. And there's also evidence for very thick lithosphere under those regions. So I think, yeah, delamination could well do the job. I think the paleoaltimetry stuff is a really interesting avenue to try and couple with the timing of the onset of extension within some of these normal faulting basins, because that might actually tell us more about this link between whether uplift happened before these normal faults started or during the timing of motion on the normal faults or after. Because you'd expect with lithostrate rate foundering that essentially with uplift you would get the onset of extension. But I think, yeah, it's a great question. And I think it's something that if we can get out and actually say something about the timing, the onset of extension on the normal faults a bit better, and we can get some, I mean, there's lots of good paleoaltimetry stuff out there now, and that's a question that we could start to address. That's a lot of work, stuff that people like Kamala Gazio have worked on, and they know a lot more about this than I do. Martin Zekra, do you have an idea why changes in the internal and fallen deformation less than 10 million years ago are such a big area along strike occurred at the same time? No, I have no idea. I mean, a lot of people have suggested this is going to be a plate-wide change in the system. You know, either a change in the horizontal shortening rates or the change in the rates of plate motion. But I have no idea, Martin. YJ Gao. Hi Sam, is there evidence that the Brazilian shield is under thrust beneath South Peru and northern Bolivia, north 9 degrees south? Yeah, good point. I think there is some kind of subtle evidence that is the case. So there was some work that came out from body wave tomography and coupled with surface wave tomography in the region that sort of suggests there must be something relatively fast underneath the eastern margin of the Andes, but there's been no real decent geophysical, at least seismological deployments that actually cross that edge of the mountain range. There's a whole bunch of interesting stuff going on along the eastern side of the Andes that would be great, at least in southern Peru, northern Bolivia, that would be great to go see. There's some of the steepest topographic gradients on Earth along the edge of the Andes in northern Bolivia. They're the same topographic gradient as the Longmen Shan, which everyone lauds as being the steepest mountain, the highest relief change on Earth. And yeah, it would be really interesting to actually map the extent of Brazilian shield underthrusting along that whole section of the mountain belt. But I do think it probably is underthrust in that region just because there's very few earthquakes, and that's telling us that the deformation is predominantly accommodated probably within either a relatively aseismic shallow layer or along a decollement that's kind of prepared to rupture, if you like. Whilst in the sections where the Brazilian shield doesn't look like it's underthrusting, you're probably all those lower crustal earthquakes in central Peru and in the Sierra Pampeanas is telling us that it's kind of either pre-rifted material that's shortening today, or it's, you know, you're looking at the edge of some kind of passive margin that's been shortened, not a cratonic material. So Manfred Strecker, interesting. In Bolivia, you focus on normal faults, and it appears that they have affected a very extensive area. Is there evidence for isolated pockets of protracted shortening that continued in the flat area in the period this can be observed? Yeah, I think this is a really interesting, really interesting point. Is like, so a lot of the really early work in this area interpreted far more changes in the deformation state within these regions, far more over shorter timescales. So the work of people like Michael Sebrier and Mercier, and down in the Puna section too of the Andes. I am slightly curious about some of these things, just because lots of the changes in the deformation state within these isolated basins, you know, you're just looking at the sort of folding of sediments within a basin at that point. These things are kind of swimming around on the sediments underneath, and whether that's actually coupled to the large-scale deformation of the crust is always a little bit unclear. So a lot of those observations from those early studies, I mean, I don't know about the ones that Manfred's talking about here, are often, you know, metric scale offsets along faults within really local little isolated you know, sedimentary basins. So I think it's difficult to I mean, given that we don't really see the flat slab changing the dynamics of the modern day mountain range, as far as I can tell, it's difficult to understand why the flat slab previously would have changed the dynamics, you know, the sort of state of compression versus extension, for example, within the ancient mountain range. And I think that's an interesting thing to think about, is like what we need to think more about, what we can see going on above modern flat slabs if we want to invoke things about what happened above old flat slabs. One from Marcos Tranos. As far as I understood, you mentioned that the effective friction is very small. Yeah. However, I have not seen this to be reflected to the fault activation, since mainly normal faults of more or less than northwest-southeast strike have been activated. Why do we not have this variation in the calculated node planes of the earthquakes? That's a really good point. So I was talking about the faults within the South American lithosphere, where the effective friction is presumably relatively small. I guess it depends on the ratio between the forces or the stresses that are available to deform that stuff and their strength. So it doesn't necessarily just depend on their absolute strength. It depends on the difference between the strength of well-oriented faults and poorly oriented faults, if you get what I mean. And also what we see is a lot of the deformation that we have on the western margin of the eastern margin of the Andes seems to be reactivating previously active rifts that were trending sort of sub-parallel to the modern range strike. So you'd expect those faults to be roughly well-oriented, if you like, i.e. parallel to the modern eastern margin of the mountain belt. So that's probably why there isn't a great deal of variability in the strikes of active faults on the eastern margin of the Andes, is that actually the faults that pre-exist within the lithosphere are well-oriented for reactivation. Okay, and then Jonathan's told me to shut up, so that's...
Yeah, I'm back again. So I guess I'm going to actually ask the last question. Can you just speculate a little bit on the lack of seismicity across the widest, sort of the central Andean fold and thrust belt in southern Bolivia? Like you mentioned that there's no seismicity, including on the Altiplano, but also in the sub-Andes you have very little. And this is a place where your model would perhaps suggest active normal faulting. You also don't see any thrust faulting or much of it in the fold and thrust belt. Despite it, there's evidence that it's rapidly compressing 10 millimeters per year, and all the crustal shortening is happening there. Would you mind speculating briefly?
No. I mean, I think it could, it could be that, like you think, like some people suggest there's an accumulation of elastic strain in that region along a decollement is just relatively small and it's going to bust in a major earthquake that breaks the decollement. I think that's a really important thing for us to consider, is that there's actually the accumulation of elastic strain in that region. It could also be that there's diffuse deformation, but when thinking about the deformation within the top of the Bolivian Andes, I kind of think that so some work that Simon Lamb has done suggested that the shortening rate in the Chorqué-Corococo basin, which is in that region where there's no active deformation, actually reduced between 10 and 3 million years ago. So if that area was slightly lower, then if it was still shortening and then you reduced the forces acting along its eastern margin, then it would switch between a state of shortening to no deformation and in this state of plateau formation, if you like. So it's just that probably the South Peruvian section, which is currently higher, it's about 300, 400 meters on average higher, was higher. So any change in the force on the edge of the mountain range, small change, would have been easier to lead to the onset of extension, whilst in the Bolivian Altiplano, given that it was lower and it was still shortening, any change in the force on the eastern margin of the mountain range would have maybe led to a stage where it switched between shortening to no deformation, i.e. strike slip. And there is evidence that there's strike slip faulting in that area from, there was that magnitude 6.6 earthquake near Cochabamba. But I mean, really, yeah, I think it's still kind of unclear why there's so little going on in terms of seismogenic deformation in that region. I think that's one of a really important question to try and address. But I've not been to the Bolivian Altiplano, and I think if there are some people who have, then I mean, I've looked in that area and I can't find any evidence of big faults. Big active faults. There's nothing in the geomorphology. So I think there is a kind of explanation that's consistent with this framework for why there's no deformation there. But what's actually happening on the eastern margin of the mountain belt and how that contrasts with whether it's aseismic or whether it's accumulating elastic strain, I think is very difficult to address with with what I know anyway. Maybe someone else knows more.
Well, thank you very much for being willing to present this really wide-ranging and fascinating study of going from fieldwork to modeling to relating these observations to the geodynamics. We will, so like I said, we recorded the talk. I started the recording a little bit late. I apologize for that, but I'll probably post the recording on maybe the COMET website unless I can find, and I'll send the link to the GFZ group and to the strategy and Smurf group. So if you want to share Sam's talk with anyone else who may have missed it, and I imagine Sam would also be willing to answer questions via email. You can Google him and find his email at Cambridge. But thank you again for joining us, and thanks everyone else for attending. And with that, could end the presentation.
Yeah, thanks. Bye.
Adieu.